Now let's take a look at an example, a negative pressure example system. So we've got a reservoir, two reservoirs, right? Water's moving from A to B, and we've got a pipeline that rises over a hill. And so we have the potential for negative pressure in this system. So let's just give some basic information here. We've got a PVC pipe where diameter is 40 centimeters, so 0.4 meters. We know that the length is 2,000 meters. The temperature of the water is equal to 10 degrees Celsius. And there's a elevation difference of 30 meters between the two. So we've got this rise over the hill, and we want to determine the maximum height the pipeline can be raised at the summit above the water surface of the lower reservoir in order to reduce cavitation. So say we've got this hill, and do we need to bore through the hill? Can we just go on the surface of it? Do we need to trench it? What's the situation here? So let's take a look. What we're going to do, the way that we're going to solve this problem is we're going to think about the water at this point. We'll call this S. So instead of 2, we'll call it S. And we'll think about the water at this point, which we'll just call B. So we'll write out our energy equation. And we're going, remember, from S to B. So we'll say the elevation relative to B, so HS, we'll call it plus our pressure plus our velocity is equal to the head over here at B, the elevation head. Sometimes we write this as Z plus pressure plus velocity. And then head loss, right? So of course we can cross some stuff out, and we do know that we have pressure here. We do know we have velocity, right? We can cross out, if we set our datum to be right here, then we'll cross that out. And we can also cross out our velocity and our pressure because we're going to evaluate it at the water surface there. So our point B will be right there. Moving on, we can set our pressure term here, pressure head term, to that standard kind of rule of thumb value. So we said that was about 2/3 of the atmospheric pressure, which was -10. So that gives us -7 meters. So this is just an assumption. This will be just a design standard here that we don't want our pressure head to go below -7. If it goes below, it's getting close to cavitation. So we'll have whatever that elevation is, that rise of the hill, which is what we're calculating, which we want to calculate. We have our velocity head, and that's going to equal to the head loss. And so our head loss, of course, we'll go to Darcy-Weisbach here, and we also need to account for minor losses. So we'll do, for our head loss, first we'll do the major losses. So we'll do the friction factor times length over diameter, V squared over 2G, plus, in this case, our only minor loss is between here and here is this exit. And so that k exit times v squared over 2g. So we'll take out, we'll put in some values and we'll take some stuff out. We'll have our f times, in this case, I didn't say, but we know that this hill is 1,000 meters away. So the whole length is 2,000, but this length right here is 1,000. That's our diameter. K exit is always 1. And then we can take out the velocity squared over 2g because it's going to be the same. So now we've got the head, the elevation at S minus 7 meters, which is our design standard for the pressure head, plus v squared over 2g is equal to the head loss, which is the major losses right here, plus the minor loss. It's just that exit times v squared over 2g. So obviously we need this velocity. We don't know the flow rate. Let's take a step back and say, okay, how do we calculate the flow rate? Well, this is just a type 2 problem from our previous work, previous week, where we know the elevation difference between the reservoirs, we know the pipe characteristics, and so we need to use the Moody diagram, etc., to calculate head loss and ultimately determine our discharge through the pipe. So let's do that real quick. We'll write out our energy equation, and so we're going to do, this is a type 2 pipe problem between A and B. So we'll do HA, in this case, that's the elevation at A, plus PA over gamma, plus VA squared over 2G is equal to plus head loss. Let's cross some stuff out because we're going to evaluate it at the surface of the reservoir. We'll cross all those terms out. So A will be just right here. So no velocity, no pressure. And we can say that delta H or delta Z is equal to 30 meters, which is equal to our head loss. And head loss, let's unpack that, is equal to our major plus minor losses. So let's go back and look at what we have. We have an entrance, we have the major losses, and then we have an exit. So we'll have K entrance plus F L over D plus K exit times V squared over 2G. So minor loss, major loss. And you'll note that F L over D times V squared over 2G is the Darcy-Weisbach equation, and then K times V squared over 2G is our minor loss equation. So now we're just adding these up, multiplying it by V squared over 2G. Now, we've got this problem. We know most of these values, except we don't know F. We can go and assume fully turbulent flow. We can do E over D from the Moody diagram and do that iteration. So I'll just run through that super quick. Our E over D is equal to 0. Oh Lord, 1, 2, 3, 4, 5. 0.375. So it's basically a smooth pipe that's going to be at the bottom of your chart there. It might be off the chart, in fact. So you go to the bottom of the Moody diagram, you get an F. If you go straight across, assuming fully turbulent, 0.015. That gives you a Reynolds number of 8.5 times 10 to the fifth. If you then go back and get a new F based on this Reynolds number, you'll find that your new F is equal to 0.012. So you have to do another iteration there, and you end up with F is 0.012. So what that gives us then is a velocity by putting that F value in. You got 30 meters over here. You got your K entrance, K exits. I think I'll just back up super quick and do those numbers. So if we do 30 meters right here, for the entrance, we'll assume a square edge, so 0.5 plus 0.012 times 1,000 meters over 0.4 meters, plus our exit coefficient, which is 1, all times v squared over 2g. So if we solve for v, we get v is 3.09 meters per second. All right, now we can go back up here and solve for HS. And we'll remember that HS is this rise, this elevation that the pipe can take in order to avoid cavitation above the surface of that reservoir B. So HS is equal to 7. Plus, and then our major and minor losses, we know that our F is 0.012, our length over our diameter, plus our exit loss, all times v squared over 2g, and then we brought over that other v squared over 2g that was on this side over here. So if we plug in our 3.09 meters per second here and plug in gravity here, then we end up with our HS is equal to 21.6 meters. So let's just review what we did. We had this pipe flow problem, and really what we could have done first is just say, okay, here's the two reservoir elevations, here's the pipe characteristics, let's solve for the flow rate. The new thing that we did here was we added the minor losses at the entrance and exit, and then we did the major losses. This was a type 2 problem. We had to do an iteration to ultimately get the minor loss to calculate the velocity. Once we had the velocity or the flow rate through the pipe, then we could evaluate the energy loss between here at the apex of the hill and the outlet of the reservoir. What that allows us to do then is say, okay, let's set the pressure in this pipe to be that design standard of -7 meters of pressure head, not quite cavitation level, right? So we're still safe. It's okay to have some suction, negative pressure in the system, but just not to cavitation levels. So that's what we wrote out here. We started with the elevation at this point S, HS, the pressure head, which we set to -7 meters, the velocity head, which we didn't know, but then we calculated from the flow rate. And we said that's got to equal to the head loss from this point to here, assuming that our datum is 0. So really we're just looking at the elevation relative to this datum, which makes our problem a little bit easier to solve. Once we calculated the velocity, it wasn't that hard of a problem. we just had to plug in velocity and then our head losses, and then we were able to solve for HS. So we said that HS is 26.1 meters. That means we can elevate that pipe to 26.1 meters above this reservoir elevation to avoid the pressure dropping too negative and getting close to cavitation.